Hello GCC, welcome to Chapter 9 Part B. This is the second video for Chapter 9. We are starting off with the pH scale. The pH scale in water goes from 0 to 14. Right in the middle is 7, so 7 is considered to be neutral. As we're moving from 7 towards 0, getting smaller, we're getting more and more acidic. So 0 is the most acidic. And as we move from 7 towards a higher number, so moving towards 14, we're getting more and more basic. Now, remember, what ion is in an acidic solution? What ion has to be in water that makes it an acid? You're correct if you said H+. So H+ is the dominant ion when we're acidic. There's more H+ than OH-. When we're neutral, the H+ and the OH- are actually equal, so in a way they cancel out, and that's why it's neutral. And then when we're basic, what ion do we have in water that makes us basic? You're correct if you said hydroxide, OH-. So that is the dominant ion when we're basic. We have OH- ions, and there's more of them than the H+ ions. So again, 0 to 14 is our pH scale, 7 is neutral in the middle. When we put brackets around a chemical, it means it's the concentration of that chemical in moles per liter. So when we put brackets around H+, it means it's the moles per liter of H+ ions. In pure water, the concentration of H+ and OH- is the same. But as we just saw, if H+ is greater than OH-, the solution is acidic. And if H+ is less than OH-, then the solution is basic. So hopefully you got those two right. When we have more H+, we're acidic. When we have more hydroxide, we are basic. So what exactly does pH mean? Well, it's a logarithmic function. Now don't worry, we're not going to do log calculations. But I do want to show you this relationship. pH equals the negative log of the concentration of H+ ions. Or we can rearrange that to H+ equals 10 to the negative pH. So when H+ equals 10 to the negative 4, then pH is 4. So that 10 to the negative number, that number is the pH. So let's look at the example. H+ equals 10 to the negative 1, or that would be 0.1 moles per liter. So the pH is 1. All right, if H+ equals 10 to the negative 5 moles per liter, the pH would be, I hope you said 5. If H+ is 10 to the minus 8 moles per liter, the pH is 8. If H+ is 10 to the minus 3 moles per liter, then the pH is 3. Good, I think you've got this. What about if we write it in decimal form? If H+ is 0.001 mole per liter, what's the pH? Well, that's the same thing as 10 to the minus 3, because we're moving that decimal 1, 2, 3 times. So 10 to the minus 3 and 0.001 are the same thing, so it's 3. And then look at the last one, 0.000000001. If you said 8, you're correct. We moved the decimal 8 times, so that is equal to 10 to the minus 8, so the pH equals 8. So there's the answers. We said 5, 8, 3, and then it was 3 again and 8 again. Very good. This is just for fun. It's the pH of some common things like vomit. Our stomach acid is hydrochloric acid, and vomit can be around 2, even a little less. That's why it burns your esophagus when it comes up. That's why it erodes your teeth when you throw up a lot. Your dentist can actually tell if you're bulimic because your acid erosion is out of this world. Lemon juice is around 2.3, coffee is around 5, not too acidic. Saliva is around 7, blood is right at 7.4. Milk of magnesia is an antacid medication. It's around 10.5. Ammonia is a cleaning agent. It's 11.7. Urine is 6. Most sodas are 2.5 to 3.5, but root beer can get up to 5.5. It doesn't have the same acids in it as most sodas. So actually root beer is actually better to drink on your teeth than soda. Alright, buffers. What you really need to know is just the definition of a buffer. We're going to explore them further in lab. A buffer is a solution that resists a change in pH even when a little acid or a little base is added to it. So what that means is it keeps the pH the same or close to the same, keeps it constant. So let's say the pH of a buffer is 4.2. You can add a little bit of acid, maybe it only goes down to 4.1. Okay, so it keeps the pH about the same. It doesn't change very much. Buffer systems are very important in bodily fluids. Our blood pH is heavily buffered. It needs to stay right around 7.4 or you can actually die. It's called alkalosis and acidosis. And if your pH in your blood gets way off, it can kill you. So buffers are important. Alright, here we see a balanced equation. 2HNO3 aqueous plus CaOH2 aqueous makes 2 H2O liquids plus CaNO3 2 aqueous. So looking at that reaction, can you tell what kind of reaction it is? You're correct if you said it's a neutralization reaction. It is indeed an acid-base neutralization reaction. So we're looking for the Arrhenius acid and the Arrhenius base. Can you locate those two chemicals out of those four chemicals? You're correct if you said HNO3 is the acid and CaOH2 is in fact the base. That is because the HNO3 has an H in it, and it's losing that H, and the CaOH2 has the OH in it, and it's losing that OH. The H and the OH come together and make, what do HOH make? Water. That's correct. HOH is water. Now, looking at the products up there, we have calcium with 2 nitrates. There was only 1 on the reactant side. Why does calcium need 2 nitrates? Why is it bonded to 2 nitrates? I hope you thought about charges, because that is correct. Calcium has a +2 charge, and nitrate is only -1. So we need to have 2 nitrates for every 1 calcium. Remember, every time you put a metal and a non-metal together, you have to check your charges. So when you're writing these reactions and you're making your salt, it's a metal and a non-metal coming together, you have to check your charges and make sure it adds up to 0. So calcium is +2, nitrate is -1. That doesn't add up to 0. We need 2 of the nitrates to go with that calcium. And that's why the formula has 2 nitrates. Alright, I want you to pause the video now and draw a picture in a beaker of water of HNO3 and what that looks like. HF, we had one earlier, let's see if you remember what it looked like. KOH, let's see if you can draw that one. And then MgOH2, we had that one earlier, don't look at it, see if you can draw that. Okay, hit pause now. Okay, I hope you hit pause and practice these beakers. Let's look at the answers. There we go, look at the HNO3. What do we notice about it? If you drew it correctly, it's all ions. That's because HNO3 is strong acid. It's a strong acid. So it's all ions. What about the HF? It's an acid because it's making H+, but what do we notice about HF? Yeah, most of it stayed together. Hopefully you drew it that way. A bunch of HFs together and only 1 apart into H+ and F-. What about the KOH? What do we notice about it? Well, it's all ions. All ions mean strong. Again, this is a strong base. Potassium hydroxide is a strong base. All ions, K+, OH-. All of them in ionic form. And then finally, we have our magnesium hydroxide. Hopefully you remembered that's a weak base. Most of it stays at the bottom, settles at the bottom in the solid state. There we have our MgOH2 at the bottom. And then only 1 broke apart into Mg+2 and then 2 separate OHs floating around. Okay, so MgOH2 means there's 2 OHs. So you have to draw one OH minus and another OH minus. Alright, so there are pictures of a strong acid, a weak acid, a strong base, and a weak base. I hope you drew those correctly. Do expect to see beaker drawings on your final exam as well as your next exam. Okay, yes, we do have beaker drawings on your final. I love the beaker drawings. So, summary. Arrhenius acids make H plus ions in water. Arrhenius bases make OH minus ions in water. So that was the Arrhenius definitions. Then we had the Bronsted-Lowry definitions. Bronsted-Lowry acids lose H plus, whereas Bronsted-Lowry bases gain the H plus. So that was an H plus or a proton transfer. Strong acids break apart and ionize 100%. Weak acids ionize only 1 to 5%, way less. Strong bases break apart and dissociate 100%. Weak bases dissociate way less, 1 to 5%. And then buffers keep pH constant. Alright, this is the end of our Chapter 9 Part 2 video. Thanks for watching.